Good, most of you are here. I didn't scare away too many people now. But hopefully we'll have a fun semester. Today we'll get into the fundamental concepts and the ISA. We'll start the ISA level. This is still introduction, so you may know some of these things, but hopefully you'll learn a lot too. A reminder, homework 0 is due next, this is not true, right? This is next Wednesday. Okay, so there's the first bug that's dynamically corrected. That should be next Wednesday, right before lecture. And homework 1 is, I'm not sure, this is Monday, this is true, January 28th. And this will be up later tonight, if not early tomorrow morning. Okay? And that will be synergistic with your lab assignment 1, which is due February 1st. Hopefully you'll have fun doing this lab assignment. It's a functional sea-level simulator for a subset of the MIPS ISA. And you'll learn about MIPS ISA in the next week's discussion sessions, recitation sessions, as well as the lab sessions, I think. We haven't decided fully yet when we will do that, but we may do it in the lab sessions. But you're more than welcome to study on your own. It's a simple ISA. Okay? Should be fun. Okay. Just a reminder, a very brief recap of the last lecture. We talked a lot about hardware and software in the last lecture, right? And how this course spans both. And I'd like to remind you, this is classified under computer hardware, but you will be much more capable if you understand the trade-offs related to both. And this lecture will cover some of that also, as you will see. If you master both the hardware and the software and the interface between them, you can develop better software if that's what you want to do in the future. And you can also design better hardware if you understand what software it will execute and what kind of programmers you're dealing with at the higher level, what kind of users you're targeting at the higher level. We'll go more into this in this lecture also. It's a fascinating topic, I think, because you're really affecting every part of the computing stack as a computer architect. Okay, and you can design a better computing system if you understand both in the end. You'll be a better computer architect. So we'll cover the hardware-software interface and the microarchitecture. Okay, I'd like to start with, we didn't make it fully clear, but I'd like to start with why study computer architecture? You guys are here taking this course. Why are you doing it? I guess you can tell me, and I'll tell you why is it interesting. To satisfy the hardware requirement? Hopefully that's not the only reason, right? To learn about how a computing system is designed? Is that your goal? Okay, good. That's a good start. So first of all, let's start with what is computer architecture. I already told you this, but it's the science and art of designing, selecting, interconnecting hardware components, and designing the hardware-software interface to create a computing system that satisfies some goals. And I think in this lecture, we're going to cover all of this. Basically, what are those goals? What are they dictated by? And how have they changed today compared to the last 50 years? We're going to do a very brief covering of that. And what are these things? Well, we will distinguish between the terms architecture and microarchitecture very soon. I did that already earlier, but we'll go into more detail today. Okay? So an enabler of computer architecture has been Moore's law. How many of you are familiar with Moore's law? Most of you. Who's not familiar? Don't be afraid to speak up. No? I'm not familiar. It's okay to not know something. So, but Moore's law, probably many of you have heard about it somehow. This is not a law in a physical law, but it's an observation that Gordon Moore made in 1965, and this is a seminal paper. Again, I'll encourage you to read that paper. It's only a 3-page paper, I think, if I remember correctly, or 4 pages maybe. Justin can verify that. Gordon Moore made the observation that he basically plotted how many devices you can put on a chip, and he plotted it over years. Like this year you can put so many devices. This year you can put so many devices. Devices could be transistors, gates, etc. And what he found out is the component counts you can put on a chip doubles I guess every other year. This is another bug here. Can you make a note of these bugs so we can so that I can fix it? So he found out that the component counts double every other year. So that's Moore's law. So what does this mean? Basically, over time, you can put more transistors on a chip, which means that you can do more things on a single chip. And this enables us to design hardware that is more capable over time, right? And this is actually an old graph from Intel's website. It goes up to 2005, and there are processors that are around that have about 1 billion transistors at that time. Today we're much more than that. Like today, I think we have processors that have 3 billion transistors, right? And I cannot keep up with that. Well, this is another way of looking at it. This is Gordon Moore, by the way, when he was young. So this is, and you can, again, it's not a physical law. You can plot it differently, and you'll get perhaps every 18 months, you get a doubling of the components, number of transistors on an integrated circuit. But this is a more general curve. You see that this is exponential, right? Y-axis is logarithmic, and x-axis is the years. And you see processors from Intel 4004 all the way to, what is that? 10-core Xeon Westmere. And that's not even state-of-the-art anymore. Okay? So this has enabled lots of transistors for us over the years. And what do we use those transistors for? What have we used those transistors for? You're reading a couple of things. How many of you have done the two readings that I assigned? Good. How about the others? You're still getting ramped up? OK. Those readings should tell you, like, what have people used those transistors for? At least an idea. I mean, it's not explicitly stated, of course, but Yale Pat's paper describes how you can use those transistors for what are the principal components. And our paper describes, at least focusing on the memory system, what have those transistors been used for. But there are many uses for these transistors, and this course will be about how we can best use those transistors for different purposes. OK. This closely ties into the question of, like, why study computer architecture, actually. What should we do with these transistors? And why study computer architecture is intimately tied, I think. And these are some of the reasons that I have. And I think this is the main reason you're here. You'll become computer architects, and you'll understand why computers work the way they do, and how you will design computers in order to enable better system designs, right? In the end, the goal is to make computers better in some way. Better could be faster, cheaper, smaller, more reliable, more robust, more predictable, maybe, depending on what you want to do, right? And the goal is to exploit advances and changes in the underlying technology and circuits. And Moore's law is an enabler to do all of this. There's another goal, which is enable new applications. You could argue that these are similar, right? Better systems come with better applications, potentially. But new applications also come without thinking about them, perhaps, right? You design a better system, and eventually someone writes an application that takes advantage of it. Some of these things are not predictable, right? For example, 20 years ago, were we able to envision lifelike 3D visualization, the kind of games we play today? Maybe you could envision it, but we didn't have it at that time, right? Virtual reality, this is still not there. Telepresence, for example. Can you be present somewhere else, or an image of you can be present somewhere else like you're there in real time? These applications are things that people can imagine, and they come because people can enable better systems by designing better computer architectures and microarchitectures. And one thing that's very interesting is personal genomics, I think. Can you design devices that you can attach to yourself, for example, that analyzes you all the time and maybe gives you recommendations on what to do? I don't know. People, once you build better computers, higher performance and energy efficient computers, people will design applications to take advantage of them. So you have a role as a computer architect that changes the future. And also, you can enable better solutions to problems, right? Maybe you don't enable new applications, but you make current applications much, much better. And software innovation is actually built into trends and changes in computer architecture. We have had performance improvements that are greater than 50% per year over time. Now, granted, this is not all due to change in architecture. Some of that is due to change in circuit technology. But this enables a big growth, big progress in the entire technology space. So these are some of the big pictures why I think studying computer architecture is important. So I guess before we move on to some of the topics, I think today I'd like to give you some perspective of where we are today in computer architecture. So this is actually a very exciting time to study computer architecture. If you were studying this maybe 20 years ago, it would have been very different when I was studying it for the first time. Because today things are changing a lot, actually. Before, like 20 years ago, there was one determined, or there was one way of designing computer architectures where people had a lot of consensus on, which is you had a single thread, and the goal was to execute that single thread very, very fast. And people have developed techniques to execute it very, very fast in hardware. And that was what everybody was working on almost in the general purpose microprocessor space. But today is very, very different. Today, the industry and research also is in a large paradigm shift to multi-core systems. It's not clear. There's no consensus on what kind of system is the best system today to build going into the future. Like we have multi-core processors today, right? But it's not clear if that's the answer because that makes life very, very hard for some people, as we discussed, programmers. And maybe there are some other things that are beyond multi-core processors, maybe dynamically reconfigurable architectures. We will talk about that at some point, maybe not in too much detail, but we'll get to that. Today, many different potential system designs are possible. So I'd like you to have that perspective going into this course. And there are many difficult problems that have motivated this large paradigm shift. And also, there are many different difficult problems that are caused by the shift also, by this change. Now, we're not improving single-thread performance anymore. Why? Well, it has become very difficult to design complex processors that try to improve single-thread performance. We'll see some of those techniques, like current processors are actually very sophisticated. People have developed techniques to extract parallelism out of single thread at the expense of a lot of energy and power consumption. For example, we will see a technique called out-of-order execution. Right? Instead of executing the program, executing the instructions in the order specified by the program, we're going to design processors that execute instructions in parallel. Now, this requires the hardware to have the ability to find instructions that can be executed in parallel, right? Not all instructions can be executed in parallel. Because if you have dependencies between instructions, you should not be executing them in parallel, perhaps. Now, how do you find instructions that can be executed in parallel? There are very sophisticated techniques to do that. We'll cover all of that when we cover out-of-order execution. But this comes at the expense of additional energy and power. And additional complexity also. So these have led to the paradigm shift. It's become very difficult to improve the single-thread performance alone. So the techniques to do that come at a cost. Now, those are very interesting techniques to research, but it has become difficult. So these are two problems that are motivating the shift. And they're also, power and energy has become inherently important because of the way the world works today, right? The world is not limited to servers and desktops anymore. Like we have these devices that require much higher energy efficiency. We did not have these 20 years ago necessarily, at least not to the extent we have them today. So there's a top-level application and user requirements that are driving this shift today a lot more. And you probably want a lot more energy efficiency out of this, right? I'm never happy with this. In fact, it's pretty bad. The energy efficiency I get out of this is very bad. I don't know what you feel, but you guys are probably much more proficient with this thing than I am. I don't play Angry Birds on it. But I understand that it's very, it consumes a lot of energy if you're an avid player. OK. So there are other difficult problems which we will talk about. For example, difficulties in technology scaling. one way we get many, many transistors on a chip, well, actually, the main way we get many, many transistors on a chip is by making those transistors much, much smaller. Right? But once you make those things smaller, there's a limit at some point. How small can you make a transistor? Right? Can you make it an angstrom? Can you make it 1 nanometer? Maybe you can make it, but will it work? Will it be reliable? Will you be able to operate it reliably? Well, will it be, yeah, basically, we're having difficulties in technology scaling. And we will talk about that. I'll give you one example, one concrete example. You guys know about DRAM, dynamic random access memory? And you know what it looks like, right? You have a capacitor, which stores some charge. And you have, this is a DRAM cell that stores 1 bit. And you have an access transistor. And this is 1 bit of storage. Whether this capacitor is charged or discharged denotes whether a 1 or 0 is stored, right? And this access transistor controls, this access transistor enables the reading of this charge. If you enable the access transistor, the charge gets shared with this bit line. I'll not go into detail. We'll cover it later on. And you can sense the charge of the capacitor. There's a sense amplifier that I'll not draw here. Now, let's say we want to put more storage on the same area. What do we want to do? We want to reduce the size of these, right? That's the idea of scaling. You want to scale the size down so that you can put more of these bits on a single chip. The problem is once you reduce the size of these two things, this becomes unreliable. In fact, it becomes very hard to reduce the size of the capacitor. The capacitor becomes unreliable, and this access transistor becomes also leaky. It leaks the charge. Now, once it leaks the charge, what happens is you need to refresh this capacitor more often, right? You've studied DRAM, right, earlier. You know that this charge leaks, so you need to periodically refresh this capacitor to be able to store data reliably. Now, once you make both of these smaller, the charge leaks much, much faster. So you need to refresh more often, which means that you need to consume even more energy. And this also becomes unreliable. Once you make it smaller, the noise margins reduce, which means that this becomes more prone to errors. It becomes less likely to be reliable. It becomes easier to flip the charge in one way or the other. So you may actually store a 1, but maybe a particle strikes, or maybe a particle strikes and it turns to 0, right? So those are the reliability-related issues that come because we're scaling the technology down, trying to cram more components onto a single circuit, trying to be on the curve of Moore's law. But that's causing a lot of problems today to us. And that's the reason for this paradigm shift today. How do we solve these problems through architectural techniques? And it turns out this is a difficult problem to solve at the circuit level, because you do want to push it. You do want to cram more components, which means that you do want to scale the size down. And once you scale the size down, you need to find some other solution, maybe at the higher levels of the stack, at the architecture level, to fix this problem. We will talk about some solutions. I don't want to go into this right now. But maybe I'll pose the question to you. Once you scale the size down, the refresh rates increase significantly. You need to refresh this cell much more often. Then the question is, how can you solve that problem at the architectural level? Well, I guess I'll throw an idea. Maybe if you don't care about the data that's stored here, if you can tolerate perhaps some error in the data, maybe you don't refresh those cells, right? Now, that doesn't work always, probably. If your data is very, very critical, for example, your bank account, the value of your bank account, perhaps you don't want to do that. You don't want the higher level bit to flip. But maybe with the lower level bits, you don't care that much, huh? I guess it depends on how stingy you are with your money. OK, but these are the kind of solutions that are potentially interesting to examine going into the future. Maybe with your bank account, it's not that interesting. But maybe with your video, it's OK, right? Maybe you don't care if a pixel in your video flips to 0 instead of being 1. Right? If you don't notice that, it's OK, perhaps. Right? So the question is, can you take advantage of such user-level perception issues to design better systems? So that's one direction in which the industry is in the paradigm shift. So these kind of solutions are being considered today. Those solutions were not even on the table 20 years ago. There was one way of designing systems, which is it has to work, and you improve single-thread performance, and technology scaling goes nicely. Now we're having problems because this is getting to the range where all of the issues are propping up. OK? OK. I guess I can cover this slide for probably 10 hours. I don't want to do that right now. But another issue that we will see in this course is memory wall gap. Traditionally, memory has been much longer latency than computation. You can do an add in one cycle or very quickly. But accessing memory, accessing large amount of storage takes a long time. And this has become worse over time because we have pushed the frequencies of the processors such that we can do computation much faster, but we cannot access memory as fast. And this is becoming even worse right now as you put multiple cores on chip, as you're seeing your reading today, right? Once you put multiple cores on chip, they're sharing the bandwidth to memory, which is a precious resource, right? Let's say you put 1,000 cores on a chip. Your connection to memory is still limited, right? Because you go through the pins. All of these cores need to go through the pins to access memory. But these pins are the precious resource. You cannot add more. Well, you can add more. It comes at a cost, at a very high cost. But at some point, you cannot add more also because these are expensive, right? These consume area. There's a limit to how many of these you can add. And you're power limited. You cannot add more because of that also. So which means that this is a bottleneck between the cores and memory. So memory is becoming a bigger problem. And how to solve this, it's not clear, again. So we'll see some solutions to that problem, both fundamental and recent solutions. And hopefully, maybe you'll develop some solutions too as you go into the future. OK. I think one thing that we've already discussed is also a programmability problem. One potential solution to all of these is to design, well, it does exacerbate some of the others, but design very simple cores and replicate many of them, right? That makes the design simple. That could improve energy efficiency, as we will discuss later. But the problem is now, if you want to get high performance, you need to be able to parallelize your code such that it can take advantage of all those 1,000 processors at the same time, right? If you cannot do that, and it turns out it's difficult to do. This is difficult to do for many problems. You won't be able to solve these different issues. So this is just to give you an idea that it's not clear how we should design the systems going forward. That's why what you get out of this course you can use in the future, hopefully, to design much better systems. OK, so there are no clear definitive answers to these problems, although I'll give you some fundamental answers. And these problems actually affect all parts of the computing stack if you not change the way, especially if you do not change the way we design systems. So the reliability issues, for example, that are propping up here could affect the runtime system, right? If there's a bit flip and you do not correct it in the hardware level, this gets exposed to the programmer. Now, is that a good idea? Probably is not a good idea for the average programmer, right? But maybe it's OK to expose the system software. OK, so there are still no clear definitive answers to these problems. So you can actually revolutionize the way computers are built if you understand these cross-cutting issues, I think, how hardware and software built, and you can change each of them accordingly. You can invent new paradigms for computation, communication, and storage, which we will see very soon, in a couple of slides, I think. And I think the takeaway is if you understand how a computer is designed and what are the fundamental problems, you can actually change how things work. I think on this note, I'd recommend this book also. I've been talking about paradigms, right? This book is actually the book that has introduced the word paradigm or made it popular. It's by Thomas Kuhn, The Structure of Scientific Revolutions. In a sense, I see a lot of similarities between computer architecture and a scientific revolution today, because this is a book about philosophy of science. But Thomas Kuhn, when he wrote this book, he said science happens in 3 stages. One is pre-paradigm science. There's no clear consensus in the field. You make a lot of observations. Maybe you design a lot of systems if you apply it to engineering. I think science and engineering are relatively coupled. But it's not clear what way you should go. So there are a lot of theories that are proposed to explain the phenomena in science. Maybe there are a lot of ways that are proposed to design computer systems going into the future, right? Multi-core, single-core, reconfigurable, heterogeneous, homogeneous. But it's not clear which one is the best. Maybe there's no best. Maybe all of them will succeed. So I see that we're kind of around here. At some point, one theory becomes dominant, and he calls this the normal science. The dominant theory is used to explain the things, or the dominant theory is used to design systems. And 20 years ago in computer architecture, this was single-core processors, improve single-thread performance with some of the techniques that we will cover, out-of-order execution, superscalar, design better pipelines, make them better going into the future. But don't think about other potential solutions like multi-core. So that's the normal science. You have a dominant theory, and if you have exceptions to that theory, let's say you have a power problem somewhere, consider it as an anomaly. It's not the main issue, right? The main issue is you improve performance. Power, secondary, right? But at some point, there are too many exceptions to the theory. The theory cannot explain everything. Now, power problem becomes huge. Reliability problem becomes huge, right? At that point, the underlying assumptions are re-examined. And in computer architecture today, I think we're re-examining these underlying assumptions. Well, I think we have already re-examined, actually. Performance is not the only way we should push forward the systems, single-thread performance at least. So I just want to give you an analogy of actually scientific revolutions. And Thomas Kuhn goes on to state that this actually happens in cycles in science. And he gives a lot of examples from different fields. I'm not going to go into that, otherwise I'll take 10 hours on this also. But I'd encourage you to read the book. This is a very good book. It's a little bit dense, but I think you'll learn a lot from it. He gives a lot of examples from science, but I think it's very applicable to engineering and computer architecture today especially. OK. Anyway, but let's first understand the fundamentals. By the way, I'm going to keep you here, I think, for 2 hours today. So be ready. We should take a break in the middle. So let me know when we're getting close to the middle. What is the middle? Is it 1:20? 1:30? OK, let's take a break at 1:30. So if I keep going, just stop me. OK. So now that I've given you the big picture, let's first start to understand the fundamentals. Because you can change the world only if you really understand it, right? You cannot change the world if you don't understand it, unless you're really, really lucky for some reason. But that's very tough. OK. Which means that you should understand the past and present dominant paradigms, if we keep going with the paradigm. And you need to understand their advantages and shortcomings. So my focus in this course will be on advantages and shortcomings of every single approach. And this will be prevalent in every lecture, hopefully, and in your exams also, and in your designs when you do your labs. The advantages and disadvantages of every single thing. You should be very clear on those. Trade-offs, basically. OK. Any questions before we jump into some fundamental concepts? Has anyone read that book, by the way?
An excerpt from it, but that's it.
Oh, you read an excerpt from it?
Yeah.
OK, cool.
I had a course last term on scientific revolution. So familiar with some of Kuhn's thinking already.
That's good. Which course is that?
8226. Joel Smith teaches it at the philosophy department.
Okay, 82 is philosophy. Okay, cool. I'd encourage you to read it. It's good to read broadly. Okay, so what is a computer? That's the most fundamental thing you can ask, right? There are three key components to a computer or computing system. One is computation. You need some elements to do this computation. The other is communication. These elements somehow need to communicate, right? And you need to store some data. What do you compute on, right? You cannot just compute on nothing. So the data is really fundamental. And this is storage, basically, or memory. And this is Jungu's depiction of what a computer system looks like, or computing system looks like. You have a computing unit, or multiple computing units. And you have memory storage units that store data. And you have some communication units that enable communication between computing units and memory, and between the computing units, and potentially between the memory storage units also. And you can divide the memory storage unit into two, potentially. You can have a memory system which contains the working memory, the things that, the data that is needed by the programs that are currently running, and the storage system which is more persistent, long-term data. You could think of this as short-term versus very long-term memory, right? It's persistent and not necessarily persistent. Okay? So in this course, we're going to cover all of this, hopefully. We'll start with computing, and we will go on to memory a lot, and we'll talk about communication as well. How do you design each of these components? This is another way of looking at it. You have basically a processor, which is computation, which consists of control as well as data path. And you have memory, which stores both program and data, and you have some I/O. And this is also I/O, actually, but this is I/O to the storage level. Okay. Are you familiar with the von Neumann model of computation? How many of you have heard of von Neumann model? Okay, that's good. You'll learn something then, many of you. So von Neumann model is another fundamental way of designing computers. Again, it's not the only way. We're going to question some of these assumptions here. But this is also called a stored program computer. And this has been the traditional way of designing computers. Stored program computer, basically stored program computer means instructions are in memory. There are two key properties of this model. One is, stored program, as I said over here. But stored program actually is has not been the most dominant property of this. The most dominant property has been the sequential instruction processing. But let's cover the stored program first. Basically, you have a linear array of memory, and your instructions are stored in this memory. That's the idea. And memory in this model is unified between instructions and data. So if you look at a memory location, let's say you have some bits. I don't know. Maybe it looks like 0, 0, 0, 1, 1, 1, 0, 0, 1. It could be instruction, or data. You don't know, right? Basically, the stored value is somehow interpreted, and the interpretation of that stored value depends on the control signals. So you could interpret this as an instruction, or you could interpret this as data. There is no fundamental distinction between instruction and data. Right? So I'll ask you the question. When is a value interpreted as an instruction? Yes?
The program counter points to it?
That's right, exactly. Or put another way, when the processor is actually fetching the instruction, when the program counter points to it. Yes? So it's really dependent on when that value is accessed in the instruction cycle. We'll cover something called the instruction cycle, or instruction processing cycle. Let's say it that way. Every instruction goes through this. And the first step of the cycle is fetch. It's really fetch the instruction. And you have a finite state machine that goes through the cycle. Fetch the instruction. Decode the instruction. Evaluate the address of the operands. And then access the operands, or fetch the operands, let me call it fetch. But this is a different kind of fetch, right? And then execute the instruction, and then store the result. So there are 6 steps. And at each point in the instruction cycle, you have different control signals. At the fetch stage, if you will, the control signals specify that the thing you're fetching from memory should be interpreted as an instruction. Right? Whereas this is a different fetch stage. At this point, the control signals specify that the thing you're fetching from memory should be interpreted as data. It's not instruction at this point. So when you access memory in the instruction cycle, instruction processing cycle determines whether the value stored as instruction should be interpreted as instruction or data. Okay, the second component property of the von Neumann model is the sequential instruction processing, which means that at a time, only one instruction is processed. Only one instruction is first fetched, executed, and completed. And only after that you move to the next instruction. And you keep going. And program counter, the instruction pointer, identifies the current instruction. You already mentioned the program counter. But a better word for it is actually the instruction pointer. And Intel has been using instruction pointer nicely, I think. If you read the x86 manual, it's called the instruction pointer. It really points to the instruction, right? You're not really counting the program. But unfortunately, we have a lot of terms that have just stuck. So program counter means instruction pointer. And program counter is advanced sequentially, except for control transfer instructions. So you start from PC, let's say, equals 10. You go to PC plus 1, PC plus 2, PC plus ... Right? It's sequential processing. OK. So I'd recommend you to read that also. But this is the fundamental paper that introduced, or von Neumann and colleagues introduced this model. It's a very long paper. But that's the basic idea. So you have stored program and sequential instruction processing. So what does this look like? Basically, you have a processing unit, you have a control unit, and you have memory. And the control unit has the instruction pointer. And in the fetch instruction stage of the processing cycle, you access, the control unit accesses memory, asserts control signals such that memory is accessed with the instruction pointer. And after some point, memory replies with the instruction, with the data in that address, which is interpreted as the instruction. It's stored in the instruction register. And then the control unit moves to the next stage of the instruction processing cycle, which is decode. And you have some logic in the data path that decodes this instruction register and generates control signals for the next stage of instruction processing. And then the control unit moves to evaluate address stage, which is done in the data path somewhere here, which could be done through the ALU. We will cover that. And then the control unit moves to fetch operand stage, depending on the instruction. Some instructions may not really need an operand, right? And then the control unit moves to execute stage, which is done in the processing unit. And there could be other registers here. And if it's a memory instruction, then the control unit can fetch either load or store data from memory. And then the result is stored. And then the control unit moves to the next instruction after that, right? It's all sequential. Any questions? This is pretty simple, right? But even this model is not necessarily the only model of processing. There's something else called Dataflow model. Are you guys familiar with this? Some of you maybe. Who's familiar? Only one. OK, good. So what we've done in the von Neumann model is an instruction is fetched and executed in the control flow order. That order is sequential, unless you get to a branch, right? When you get to a branch instruction, you may change the sequential order. But in the Dataflow model, the processing is very different. An instruction is fetched and executed in an order, in the order in which data flows. Basically, an instruction is fetched when its operands are ready. not when the program counter points to it. Now let's take a look at this model a little bit, because the trade-offs are very different. And this is a very fundamental trade-off that you make when you design your computer first. So here, control flow word is specified by the instruction pointer and sequential unless you have an explicit control flow instruction. In the data flow model, an instruction is fetched and executed when its operands are ready, when its data values are ready. So instead of, so let's say you're adding R1 to R2 and storing the result into R3. Instead of executing the instruction when the program counter gets to it, there is no more program counter. We're done with the program counter. There's no instruction pointer. The processor keeps track of whether R1 and R2 are ready. And when some other instruction, let's say multiply R1, and then let's say you have an add into R2, when they produce R1 and R2, these become ready. And somehow when both of these registers or values become ready, the computer goes and fetches add and then executes it. Very different, right? No more program counter. In this case, the instruction ordering is specified by the dependencies that happen on the data, right? When this instruction is executed depends on when its producer instructions are executed. And when those instructions are executed depend on when their producers are executed. And when those are executed depend on when their producers are executed. It's all data flow based. And each instruction in this case specifies who should receive the result, which later instruction should receive the result. An instruction can fire meaning can be fetched and executed only when all of its operands are ready, received. Make sense? Which means that potentially many instructions can execute at the same time, right? There's no more von Neumann constraint, which said that you can execute only one instruction at a time. And once you're done with it, you go to the next one. Here, there's no such constraint at the fundamental level, at the conceptual level. Because potentially many instructions can be executing at the same time. Many instructions, operands can be ready at the same time, right? Okay, which is inherently more parallel at some level. Okay, I don't know what happened there, but ignore that. So consider a von Neumann program first. Let's take a look at the data flow equivalent of this. I'm going to spend some time on data flow because I think it's a very important concept for you guys to learn. And this will hopefully be useful when you come to out-of-order execution. Because out-of-order execution will use the same principles that I'm going to describe now. Except we're not going to make the programmer specify this. The computer will automatically figure out the data flow. Okay? So this is the sequential program. I guess the individual operations do not matter that much. But the basic thing is there's a program order. And what is the significance of that? Well, it just specifies that you finish one instruction before starting the next one. That's the significance. If you look at this program, what is the significance of the storage locations? So you have some values here, v, w, x, y, z. And you have this instruction, x equals v minus w, getting values from these storage locations, right? If you think about it a little bit, these storage locations are actually used to communicate data between instructions, right? This v and w are used to communicate the operands, data values produced by this producer instruction, a plus b and b times 2, to this next instruction that uses those data values. So assuming that no one else needs those values, v and w, you don't really need to store them, in fact. Right? You don't need to allocate a register for them. If the whole purpose of these two storage locations is actually to enable the execution of this instruction, the third instruction, why not directly communicate that data to that instruction, right? So you can do that in a data flow machine. So what does this look like in a data flow machine? Basically, you can think of data flow as a graphical representation of the program. And this is the graphical representation. In fact, this is how you can program a data flow machine also. This is the same program. And this is also called the data flow graph. And you can see that the storage locations are actually arcs in this graph, right? And the instructions are actually nodes. And the nodes could be different. They could be add. Well, in this case, you have a multiply by 2 node. They could be minus, subtract, add, multiply. And the arcs enable the communication of the values between the instructions. OK, so how does this work? Basically, a node fires when both of its operands are ready, when all of its operands are ready, and produces a result which gets sent through the destination arc. And we'll see an example of this. But this node fires when A and B are ready. You get an addition. This node also fires when B is ready only, because it takes B and multiplies it by 2. And this could happen in parallel, right? And these two could happen in parallel. Depending on the latencies, you can have different kinds of execution order here. For example, if we don't have it here, but if there was a memory fetch node here, it could take much longer. But you could get different ordering of instructions in a data flow machine. OK, I guess I'll ask you this question. Which model is more natural to you as a programmer? This one? Sequential one. Who says sequential is more natural? Many people. Who says data flow is more natural? No one? OK. Well, that's good. I would also say this is more natural, actually. But is it? I'll ask you the question without answering, because I don't know the answer. But is it because of the way we're educated that this is more natural to us? Or is it fundamental to the way we operate as humans? Could be. But it's good for you to think about that. Certainly, we will cover some trade-offs related to this. One big advantage of this model for a programmer is, at any point in time, you know what the state is, right? You have a definition of precise state. Because von Neumann model specifies that you cannot execute an instruction before you finish the previous instruction. You know exactly where you are in the program, right? Whereas there were no such specification here, right? And it turns out it's a nightmare to debug for a programmer. Because where you are in the program, let's say you get a bug. You need to figure out how that bug happened. If you know the precise state, now you can figure out what bug what in the program made you what mistake you made in the program caused that bug, right? But here you don't have a precise state. You don't even know which instructions have executed or fetched and which instructions have not. And this does depend on the latencies in the system also, right? So that's the major difficulty of the data flow model if you expose it to the programmer. Okay? That's why this has been a lot more natural to the programmers, and that's why the von Neumann model has been very, very successful at the architecture or instruction set architecture level. But having said that, this is more parallel, right? Because now you can enable many instructions at the same time. Whereas if you strictly follow the von Neumann model at the implementation level, you can execute only one instruction, right? You cannot even start the next instruction. But today we use techniques like pipelining. Are you guys familiar with pipelining? Basically, think of this as once an instruction, the previous instruction moves to the decode stage, you can actually fetch the next instruction, right? You can fill the pipeline this way. But that's, if you think about it, that violates the von Neumann model, right? You should not be fetching another instruction. So we're going to see how we can, the key is keeping the appearance of the sequential execution to the programmer. Underneath, we can do something different. Right? In today's computers, underneath, the execution is not sequential. The execution is turned into this data flow graph. The computer does that. And we'll see how we do that in hardware. But the processors maintain the sequential execution model what the programmer sees as sequential execution. Underneath, it could be very parallel. Okay? So I guess let's do a little bit more on data flow. I've already told you that in a data flow machine, a program consists of data flow nodes. And a data flow node fires, it's fetched and executed when all of its inputs are ready. In other words, when all its inputs have tokens. So let's say this is one data flow node, and you could actually represent it this way at the ISA level, at the instruction set architecture level. This is argument 1, argument 2, whether each of these arguments are ready. And this is the operation. And this specifies the destination of the result, which instruction should be woken up. Okay? Where should you send your token? And this fires when the inputs have tokens. And you can have many, many data flow nodes. For example, this is a conditional data flow node. How does it work? Let's call it a branch. You have a data input. You have a control input. Control input, and you have two outputs, true or false. Control input can be false or true, and data input can be anything. Depending on the control input, the data input is passed to one of the outputs. If the control input is false, then the data input goes through the false arc. If the control input was true, then this X would have gone through the true arc. Make sense? So that's how you enable programs with conditionals. You could have relationals also. For example, in this case, you're comparing two values. Is the left arc, is the value on the left token greater than the value on the right token? If that's the case, then you send a true token out of this node. Are you guys familiar with barrier synchronization? How many of you say yes? Some. OK. I'll briefly tell you what it is, but we'll get to this later on in the lecture. The idea here is you have separate threads of control, and you want them to synchronize at some point. Let's say, I guess I'll give you a detailed example. Why not? Let's say you're actually, my favorite example is, let's say you have a book. And you want to count the number of A's, B's, C's, D's, E's, F's in that book. Right? How do you do that? You could have a separate thread for each, right? Or what you could do is you could partition. Basically, you would like to generate a histogram for every single letter in the book. Now, that's a very parallel problem. Let's say your book is 16 pages. Let's make it simple. You could divide each page and have a thread go through each page to generate an independent histogram, right? Let's say you have 16 threads. You launch 16 threads. Each of them generates a histogram, right? And in the end, what you really want to do is add up those histograms to figure out the histogram for the entire book. But you cannot add up those histograms until all of the threads finish, right? So this is one place where you want a barrier synchronization. What does barrier synchronization mean? You want all of the threads to finish before you continue doing something else. And this is the synchronization point. Make sense? This is one example. There are many, many examples in parallel programming where you want all of the threads to finish doing something, or some number of threads to finish doing something before you move on to the next stage of the processing of the program. So this is one example. And this node can be implemented in data flow also. These different threads, they have tokens. Once they have tokens, they're done. All of them are done. So this node fires when all of the tokens are ready. Now all of the threads can continue going on. OK? OK. If you didn't understand that fully, that's OK. But this is something we'll discuss further in the lecture also, especially when we get to multi-core and parallelism. OK. I guess maybe we can take the break early. I'll ask you what this program is. Now that you know about Dataflow and how Dataflow nodes behave, maybe you can tell me after 5 minutes what this program does. Would this be a good way of spending the break? I'll give you 2 minutes afterwards if you need to go to the restroom or something. But take a look. I guess I'll specify one thing. Let's see. N is non-negative. I'll specify that for you. And this is 1. Okay? And this construct may be a little bit confusing. This means that initially the value on this arc is 1. Initially the value on this arc is n. But the next time the value on this arc is not 1 anymore, but whatever comes out of here. Similarly, the value on this arc is initially n, but next time it's whatever that comes out of here. And copy means you copy the value. Greater than 0, I guess it's obvious. It's a relational, as we saw. And copy branch, we've already seen that. Dec means decrement. This is multiply, and this is the output. So I guess what I ask is, what is output in terms of the function of the inputs? And inputs are 1 and n. And output should be a function of 1 and n, I assume. Okay. I'll give you some time. Maybe I'll take a break while you're looking at it. It's what? Oh, ground. Oh, I didn't specify what ground is. Ground means the token dies. Basically, it doesn't get communicated anywhere.
So that's like for n 0 or less, I guess, when you start out?
I don't know. I'll be giving giving out the answer maybe. But ground means let's say this branch. So you get a token here, and this Boolean specified false. The value here basically doesn't get communicated anywhere. That's what it means.
Where does control flow come?
The result is discarded. Well, control flow hopefully is controlled in some other way. I'll ask you later. So who says it's Nfactorial? I've heard Nfactorial from many people. Okay, what other answers? Anybody? So Nfactorial is the right answer, actually. I'll walk you through it, and then we'll take a break for a couple minutes because I want to still continue. Basically, what happens is initially, the principle is very simple, right? If all of the tokens of a node is ready, that node fires. Now let's take a look at, and I told you initially, these arcs have tokens on them. They're ready. So initially you have this 1, it's ready. Can this, the question you should ask is, can this branch fire now? No, right? Because this Boolean control input is not determined. So we have a dead end. Let's look at here. This input, oh, it's ready, right? N is ready, and it can fire because it's a simple copy. It has a single input. So now you have this value n output here, and the value n also goes down here. This cannot fire because its control input is not ready, but this can fire. Now you have n, and this node tests if n is greater than 0. Let's assume n is greater than 0. Here's where trial and error comes in. If n is greater than 0, what you get here is true, right? So now you have true. True gets copied. This node fires because it's a single input. Now you have true on both of these Boolean outputs. Now this node can fire and this node can fire. Now let's remember what we had here. We had 1, we had true, which means that this 1 goes through here, right? It doesn't go through here because it's a true output. Here we had n, and we have true again, which means that this n goes through here. Now in this output we have 1. Well, this fires afterwards, so you have n and n. Now you have n here and 1 here. So this node fires 1 times n. You get n here, right? We had n here. We decrement n. Now we have n minus 1 here, right? So you have n minus 1 and n. So where does n minus 1 go? Over here. And n goes here, right? So let's do the next one. Next one, you have n. This is n minus 1. You copy n minus 1. This is n minus 1. This is n minus 1. This fires. N minus 1 is greater than 0. Let's assume it's greater than 0 again. So you have n minus 1 here. Oh, this is true here, sorry. N minus 1 is greater than 0, so this relational leads to true. This true gets copied. You have true here, which means that the output of this is n, because remember, this was n. So this is going to be n, and this is going to be n minus 1, right? So n minus 1 goes down here. N goes down here. Did I do a mistake? No, you're good. OK, I'm good? Right. So this is n minus 1. Now you have n times n minus 1 here, right? And this was n minus 1. You get n minus 2 here. So now you're getting the hang of it, right? You have n times n minus 1, n minus 2. The next iteration, if you will be you'll have n times n minus 1 times n minus 2 here, and n minus 3 here. So you'll go on until this condition becomes false. When does it become false? It becomes false when this is 0. Right? And let's take a look at what happens when it's 0. You get these booleans as false, which means that your output will be whatever is here, which is n factorial. Okay? And this value dies. That was your question here. Because you don't care about that value at that point. And actually, you don't really care about that value. Okay? It's pretty simple, right? It's not the best way of implementing factorial in Dataflow, by the way. It's very sequential, right? But this gives you the concept. OK, should we take a break for 3 minutes? OK, let's take a break, and we'll continue after that. OK, hopefully this was interesting. Now you've learned the first trade-off that I wanted to cover. This was a trade-off, right? At the ISA level, instruction set architecture level, do we do control flow, von Neumann, or data flow? Or put another way, do we need an instruction pointer in the ISA? If your answer is yes, automatically you're a control-driven sequential execution von Neumann computer, right? And we already discussed what that means. If your answer is no, at least one way of designing such a computer is data-driven parallel execution, right? Data flow. And you've already seen a very good example of data flow at the ISA level. Remember, what does it mean at the ISA level? Instructions are specified to be data flow, no program counter. There are many, many high-level trade-offs related to this. I'm not going to cover all of them, but we've already discussed one of them. Ease of programming, for example, for average programmers. Many of you said that it's much more natural for you to do the sequential execution. And that becomes very, very important, especially when you're debugging the program. Ease of compilation, you can think about that. Performance, which one is higher performance? Well, inherently, data flow exposes more parallelism, right? So maybe it's easier to achieve higher performance. Maybe in the end, you can design a system that has similar performance with data flow and control flow. But it's easier to do that with data flow, potentially. Hardware complexity. Well, I'm not going to get into this, but if you actually design a data flow machine, it turns out it becomes very complex to design these things. People designed data flow machines in the 70s, 80s, up to late 90s, and even early 2000s. It was tapering off in the early 2000s, but some of these machines were very complex. One of the issues was, it turns out that in many programs, this data flow enables lots of parallelism. Lots of parallelism means that actually you need to keep that state somewhere. So whether or not you have tokens in those arcs, the hardware needs to store that somewhere. And which arcs have tokens, which arcs don't have tokens? Imagine a program that has 1 million nodes, or tens of millions of nodes. Where do you store that? And it turns out this was a problem in those machines. The hardware complexity of storing those tokens became hard to control. So people actually tried to develop mechanisms that throttle the data flow nodes. So you don't enable more than some number of nodes to be active at the same time. So you need to manage those resources, which adds more complexity to the system now. So there are interesting trade-offs related to this. We'll not go into that. But if you're interested, I'll give you some references. So we've seen data flow at the ISA level. But a similar trade-off, control versus data-driven execution, can be made at the microarchitecture level also. At the microarchitecture level, so ISA, we will cover again, but specifies how the programmer sees instructions to be executed. Right? ISA is at this higher level, with the hardware-software interface. Whereas microarchitecture specifies how the underlying implementation actually executes instructions. And these do not need to be the same. You can have a von Neumann computer that executes instructions in data flow order. Right? So in many of today's systems, programmers sees a sequential control flow execution order, versus programmers sees a data flow execution order. This is not done in many of today's systems. It has not been a successful experiment, at least in the last 4 decades. Whereas what has been successful is having the microarchitecture execute instructions in an order that's different from what is specified by the ISA. Basically, microarchitecture does something different, but doesn't expose that to the programmer. As long as the microarchitecture obeys the semantics specified by the ISA, when making the instruction results visible to the software, to the programmer, to the user, then it's OK. You can get high performance that way. Right? You can execute 10 instructions at the same time, as long as you commit those instructions one by one when you're making them visible to the programmer, such that when the programmer is debugging the program, they see only one instruction committed at a time at the control flow order specified by the ISA. It's OK. Right. Make sense? OK, we'll see how that's done. But if you want to learn, we'll get back to the von Neumann model from now on, and we'll assume that for a long time in this course. But if you want to learn more about data flow, this is the first paper, Jack Dennis and Misuna's paper, that introduces some of the basic data flow concepts. It basically shows you those data flow graphs that I showed you earlier. And this is one example computer. This paper is a little bit hard to read, but this is just to show you that people actually have built these data flow computers that operate at the ISA level. It's the Manchester computer is one of them. There have been a lot of efforts all over the world. There were quite a few Japanese companies that actually built these data flow computers. And they were used in different ways, but they've never been commercially successful. OK. So von Neumann model, let's consider this in more detail now. So all major instruction set architectures today use this model. And you're familiar with some of these probably. x86, ARM, MIPS, Spark, Alpha, Power. If you look at that, it's all control-driven, sequential, stored program execution. But underneath, the execution model of almost all implementations, the microarchitectures, is very different. None of them strictly implement the von Neumann model because the computer will run like a dog, if that's the case, right? For example, pipeline instruction execution was first used in Intel 8486. Multiple instructions were fetched and executed at the same time in Intel Pentium. Out-of-order execution was first successful, very successful commercial implementation was Intel Pentium Pro. There were other implementations from Motorola. In fact, out-of-order execution in not so commercially generally successful, that was developed in the 1960s, and we'll get to that. We have separate instruction and data caches, right? Even the linear memory with instructions and data interpreted based on when you access the control signals is different today. Instruction and data caches are separate. You could argue that that contradicts the von Neumann model. But underneath, we're not exposing any of this to the programmer. Yeah, I think I've already said you this, told you this. What happens underneath that is not consistent with the von Neumann model is not exposed to the software. That is the difference between ISA and microarchitecture. I've already given you this, and I'm not going to go over it again, but the definition of computer architecture that includes ISA plus implementation is what I told you earlier. But the traditional only ISA definition is the attributes of a system as seen by the programmer. Basically, what the programmer needs to know about the interface. So let's take a look at that. ISA, it's really the agreed upon interface between the hardware and the software. This is what the software and the compiler can assume the hardware can provide. It's a contract, right? Hardware provides this. In other words, what the software writer needs to know to write and debug system and user programs. On the other hand, microarchitecture is a specific implementation of an ISA. It's not visible to the software. And we'll see examples of this. I'll use the term microprocessor also. When I talk about microprocessor, it consumes ISA, microarchitecture, and circuits. So a more traditional definition of architecture is really the ISA, but we'll be a little bit more liberal here. When I talk about architecture, it's going to be ISA plus microarchitecture. And when I ask you about ISA, is this part of the ISA or is this part of the microarchitecture? Then I'll specifically say ISA. So let's take a look at some examples. So basically, you can think of ISA as bridging the gap between the programmer and the microarchitecture. So what is part of ISA versus microarchitecture then? There are many analogies, but one analogy is the car analogy. Right? A car has an interface to the driver, right? And that interface is reasonably constant across different cars even, right? You could argue that different cars have the same ISA, instruction set architecture. Gas pedal is one example, right? Gas pedal, you push it down, and the car accelerates. You pull your foot off the pedal, and the car doesn't accelerate. And that's a nice interface. Underlying implementation, well, that implementation of acceleration, how that gas pedal, how the car accelerates can be very, very different, right, from car to car. Some car goes much faster, accelerates much faster, and how the mechanics works is different. Versus in other cars, it's very different also. And the programmer gets exposed to that, right? So that's an example. But the interface is the same. So similar, you can have an add instruction versus an implementation of the adder, right? Add instruction, what the programmer cares about is you have this add interface. You add two registers, let's say. Our source 1, our source 2, and our destination. The programmer writes this, but the underlying implementation can be done in many, many ways, right? It could be, I hope you've seen some of these. It could be a ripple carry adder. Are you guys familiar with the ripple carry adder? OK. It could be a carry lookahead adder. How about that one? You've seen this in 240? OK, good. How about bit serial adder? Have you guys seen that? No? This is the simplest adder you can do, right? OK, I guess I'll go through the bit serial adder since some of you have not seen it. But the idea is basically, let's say you're adding two values, two 32-bit values. Ripple carry adder, you have 32 adder units, right? Each bit is added in parallel, except the carry is rippled, propagated, right? So you have, I guess, bit 0. Let's say A0, B0 if you're adding A and B. This is bit 0 of each. And then A1, B1, bit 1 of each. Dot, dot, dot. A31, B31, bits 31 of each. And this is done in parallel, except carry is propagated. Bit serial adder, you don't have 32 of these adders. You have only one, right? And what happens is you start with A0, B0, feed it, latch the result, and then shift it. And then feed it back. Make sense? It's bit by bit. Every cycle, you add one bit from each value. It's simple, right? Even that's a trade-off. What's the trade-off? This adder implementation, a lot of hardware. This adder implementation, well, maybe almost 1/32, like 3% of the hardware cost of this one, almost. Maybe 5%, let's say, because you have some additional logic here. Right? So low cost, high cost. Slow, fast. And people have used bit serial adders. We'll get to that. In very parallel computations, you don't necessarily need to design an adder where latency of an add is not important. If the latency of an add is not important, you don't need to design sophisticated adders, right? Carrier lookup is not the most sophisticated adder today. There are many adders that have been developed to be fast. If you can tolerate that an add takes 32 cycles, it's OK to have this maybe, right? Does that make sense? So this enables trade-offs now. Now we're enabling trade-offs. These different implementations give you different ways of doing this. But the programmer doesn't care, right? That's the ISA. Add instruction is the interface. Adder implementation is in microarchitect's toolbox. Now you have this toolbox to design a system that is best fit for what you're trying to do. So one example of a machine that had bit serial adders is a connection machine. You can read about this, and I think we'll get to that at some point. It's from Hillis. It had 64,000 bit serial adders. So you could do 64,000 adds at the same time. This is late 80s, late 1980s. Why? Well, this was designed for scientific computation, where you're adding huge matrices, let's say. Huge matrices mean that you have lots of parallelism in the problem, right? You have lots of additions to do. And you don't really care how long each addition takes, because in the end, you need to finish all of them. It doesn't matter whether one add takes 32 cycles or 1 cycle. But you have so much parallelism that you can do 64,000 of them in parallel. So how can you do all of that in parallel with simple hardware? Simple hardware is important. This is complex, right? Propagating that carry is actually complex. And you have, yeah. So that's, you get the idea. You can read that paper if you're interested. OK. Similarly, now let's raise the abstraction level. This is only a single instruction. But if you have a collection of instructions, let's say x86 ISA, has many, many implementations, right? 286, 386, 486. Do you guys remember any of these? Or maybe you're too young to know what a 286 is. There's also 8086, but I didn't put it over here. But these have very different implementations of the same ISA. They core, and I cannot keep up with this. So you can add the dots probably. I can add the backward parts. But yeah, so the microarchitecture is a particular implementation of an ISA. And OK, you can look at the adders in each of them. As a consequence of this, microarchitecture usually changes faster than ISA, because it's really an implementation. There are few ISAs in the world, and some of them are actually alpha, for example. How many of you know about the alpha ISA? If I asked this question perhaps 15 years ago, there would be more hands, right? Because alpha was not a dead ISA at that point in time. I don't know if anybody is designing alpha processors today. But alpha is a very clean ISA, actually, from Digital Equipment Corporation that we're going to see some features of. But this is a dead ISA now. But there are few ISAs and many microarchitectures. Many microarchitectures, examples here, right? Actually, x86 or ARM has many potential implementations, right? So why is that the case? Why does microarchitecture change faster than ISA? Or why does ISA not change as fast as microarchitecture, you think? Yes?
It has to write in your compiler every single time.
That's right, because it affects the programmer, right? It affects the software stack. Whereas implementation, you can change. You have this clean interface. You can change the implementation without affecting anything else up higher in the stack. Whereas if you change the ISA, you have to write a new compiler. The programmer needs to be aware of that. You have to write a new operating system also. OK. So what is an ISA? Actually, it's not only the instructions. An ISA is much bigger than instructions. Instructions have, we'll cover these in the next lecture, but instructions have opcodes, addressing modes, data types, instruction types and formats. Those are part of the ISA. How many registers, whether you have condition codes. We'll cover some of these next, in the next lecture. How is memory organized? What is the address space? What is the addressability? How are instructions or data aligned? Do you have virtual memory or not? How is that virtual memory managed? That's all part of the ISA, and we'll cover virtual memory. How are interrupts and exceptions handled? How does the processor handle that? How are calls handled? How are priority and privilege levels handled? Access control. How is I/O done? Is it memory mapped or is it instruction based? These are all parts of the ISA. How are going into a more multiprocessor domain, how are tasks and threads managed? How is power? How is power managed? And maybe even thermals managed today. Dynamic voltage and frequency scaling, for example, you may have heard of. That is part of the architecture of a system. Maybe you can call ISA, doesn't specify all of it, but when I say ISA, these will be part of, these are things that are visible, that should be visible to the programmer. Right? And the system programmer needs to know how to do voltage and frequency scaling. Right? This is exposed to the programmer. Although, do you have to do it that way? No, not necessarily, right? You could have a processor that dynamically scales the voltage and frequency, changes the voltage and frequency, without exposing that to the programmer. This is a choice that's made by the designer of the system that they wanted to expose this to the programmer. Right? Why? Because maybe software has more information to control this voltage and frequency. But you don't have to do it that way. Right? Again, some of these choices are made by the architect. What you expose and what you not expose is made by, depends on you if you're designing the computer. How do you handle multiple threads? How do you handle multiple processors? Those are all parts of the ISA. And this is one of my favorite books, actually. It's not only a single book that has multiple volumes. And these are up, right, Jungo and Justin? Yeah. You can view these. And you'll learn a lot from these manuals. It's a beautiful definition. x86 is one of the more complicated architectures today. But we'll see much more complicated architectures in the next lecture. It's called the VAX. OK. Microarchitecture is the implementation of the ISA under specific design constraints and goals. And we'll get to that in the next few slides. This is basically anything done in hardware without exposure to software. Again, this is a choice. You could expose every one of these things to software. And let's go over some of these just as an example. Let me see first how we're doing here. OK, we're doing well. So pipelining, for example, normally not part of the ISA. The programmer has no idea what pipeline stage there is in the machine. Right? In fact, exposing this to the programmer may be a very, very bad idea. Right? Because what if you want to add one more stage to your pipeline? Now everybody needs to write a new compiler, change their programs. Bad idea. Right? And we will see some choices made in the past that expose this to the programmer. It's what? Well, you can remind me when we get to that. But one example is a branch delay slot, for example. But we'll get to that. In-order versus out-of-order instruction execution. Again, with one Neumann model, is this exposed to the programmer? No. Right? Out-of-order execution is done underneath. You could potentially expose it again. Right? Memory access scheduling policy. Is this exposed to the software? Is it part of the ISA? Normally, no. But potentially, you could expose this also, right? If there's an advantage in doing so. Speculative execution. Are you guys familiar with this? This is basically doing things before they're needed. For example, predicting a branch or prefetching some data from memory to the registers, let's say, or the caches. This is normally not exposed to the programmer. Normally not part of the ISA. Superscalar processing, which we will cover also. This is basically the idea of fetching multiple instructions in a cycle. Again, normally not exposed to the programmer. But there have been processors that are designed, which we will cover again, that can fetch multiple instructions per cycle in a way that's specified by the software. These are called VLIW architectures, very long instruction word architectures, in which an instruction specifies multiple operations, or multiple instructions, let's say. And the compiler packs multiple instructions that can be executed in parallel into this long instruction word, and the hardware can execute them in parallel. Compiler ensures that they can be executed independently. So that's, in that case, those multiple instruction fetch is actually exposed to the programmer. It's part of the ISA. With superscalar processing, it's not part of the ISA. The hardware fetches multiple instructions per cycle, but the programmer's view is only one instruction is being fetched. Clock gating. Are you guys familiar with that? Basically, if you're not using a logic block, you turn off the clock to it. Why? This reduces your dynamic power consumption, right? Is that exposed to the programmer ISA? Normally not again, right? But you could imagine cases where you may want to expose some of this at least at the coarse grain, right? And in fact, there have been proposals that, research proposals, that expose clock gating mechanisms to the compiler, such that the compiler can say, oh, I'm going to get into this piece of code where, let's say, I'm never going to use the floating point unit. So I'm going to send an instruction that says, turn off the floating point unit. Right? So you could imagine how these things can be exposed to the software to take advantage of some knowledge that's not available to the hardware. Right? Caching. We'll cover caches a lot in this course. How many levels you have, what is the size of the cache, what is the associativity, what is the replacement policy, are these exposed to the programmer? Normally not. Now, can you do better if you expose them? Yes, you could do better. In fact, caches are actually, in some ways, exposed in the sense that we have prefetch instructions in the ISA, in many ISAs today, that specify that a value that's fetched from memory should be placed in a particular caching level. In that sense, caches are already part of the ISA. But in a sense, it's part of the ISA in a soft way, because there's no guarantee that, when we get to the prefetch instructions, I'll show you that there's no guarantee in many of the ISAs that when you issue a prefetch instruction, that data that's fetched from memory will be placed into the cache. We'll get to that. It's OK if you didn't understand that yet. Voltage and frequency scaling. Is that exposed to the ISA? Now we're getting into the interesting domain, right? Maybe you want that to be exposed to the programmer, as we said. Error correction. Well, when there's an error, somebody needs to know in the system, right? Let's say the hardware detects the error. Can it handle the error automatically? It may be the case that it doesn't handle the error. Right? In that case, it could expose this to the ISA. Right? It could expose this to the programmer. And there may be a software routine that handles the error. OK? OK, but there are some things that are clearly not exposed. But it's also good to be open-minded. You can expose everything also. Again, as an architect, you're determining how easy or hard you're making life for the hardware designer as well as the programmer. Let's take a look at some examples that are more clear-cut. Which one is a property of the ISA versus a property of the microarchitecture? Let's take the first one. Add instructions opcode. ISA. That's clear, right? Some programmer needs to know this to be able to write programs. Number of general purpose registers. ISA again. Right. Yes? Not every programmer. Remember, ISA is the contract between the software and the hardware. But some programmer needs to know that, which means the compiler writer. Right? That's right. Not every programmer needs to know because we have this huge computing stack. But ISA specifies what at least one programmer needs to know. OK? Number of general purpose registers for the same reason. Because somebody needs to compile into this ISA. Right? Number of ports to the register file. Microarchitecture, right? Here, again, you can make the choice of exposing to this programmer, but that will make your life very hard for the programmer as well as the hardware designer, because what if you want to add one more port to the register file later on? The entire stack needs to change. Right? Number of cycles to execute the multiply instruction. Depends, I heard. Okay?
On big chips, the UART, on little chips, the ISI.
Little chips. What is that?
And also X or something.
What is it?
Okay, microprocessor.
Okay, Mike. So actually, the answer is correct. It depends. You could expose this to the programmer. And in fact, for example, the VLIW architectures have exposed the latencies of each instruction. Because what does the compiler need to do? The compiler needs to be able to know the latencies of each instruction to determine when an instruction is ready to be scheduled. Right? This is all purely statically scheduled. If you don't know the latency of an instruction, you cannot know whether the values of an instruction are ready. Right? So in this case, it depends. In most of today's architectures, at least in the general purpose domain, like the x86 architectures, this is not part of the ISA. Now there's something else. This is not part of the ISA, but there's something called the hardware reference manual, or for the if you want to optimize your programs, sometimes manufacturers describe how long it takes to execute an instruction as part of a hardware reference manual for a particular implementation. In that case, they tell you how long it takes. But again, you don't have to know this to write programs in most architectures. But there are some architectures where you can expose this. Okay, whether or not the machine employs pipeline instruction execution. ISA or microarchitecture? Microarchitecture again, right, in this case. But again, you could expose this to the ISA, but it's not normally done. Because if you add another pipeline stage, well, you actually rewrite your compiler. Okay. So microarchitecture is the implementation of the ISA under specific design constraints and goals. And this ties into design points. Basically, you have a set of design constraints and their importance. This leads to trade-offs in both ISA and the microarchitecture. What are these considerations? You're reading a paper that describes this in a nice way, I think. The Yale Pat paper on requirements, bottlenecks, and good fortune. There are many of them. I'll not cover all of them, but when you're thinking about how to design a computer, you consider cost, right? That's very important. And the choices you make, we've just seen one of them, right? This determines your cost. Even a simple adder choice. Right? Whether or not you employ pipelining determines your cost. Whether or not you employ out-of-order execution determines your cost. Whether or not you design a data flow computer at the ISA level determines your cost. Performance, maximum power consumption, how much power you can supply to the system. Energy consumption, availability, how long your system is supposed to run without interruption. Reliability and correctness, time to market, all of these are considerations when you're designing a computer. Right? And these considerations lead to trade-offs. And whatever you do in the ISA and microarchitecture determine where you end up in these complex design space. And it's very hard to predict, right, sometimes. How do you model this? And design point is determined by the problem space or the application space, which is perhaps in turn determined by the intended users and the market of your system. Right? In some markets, it may be OK to design this VLIW processor. And these have been very successful in, for example, digital signal processing engines, where you have a very limited set of programmers that can actually optimize their code quickly when you change how many instructions you can fetch at the same time from one implementation to the other implementation. So your design point determines a lot of things. And, well, design point is determined by your application space, right? Let me see where we are. Oh, we still have 10 minutes. Good. Design point is determined, but I think we'll end early. Again, I can talk about this for hours and hours, but I'll let you dream of this and read the paper. If you have questions, we can talk about it. And we'll cover a lot of these as we go through the course. So application space this is from the paper you're reading, so I'm not going to cover this, but there are many, many examples of application space, and this is not comprehensive enough also. For example, I'll pick one. Guaranteed delivery applications or real-time applications that require the result of a computation by a certain critical deadline. One example, in your car, you have a automatic brake system, right? ABS system. This is a very real-time constraint. You have to design that system somewhat differently from the way you design this system, perhaps, right? You don't have a whole lot of real-time constraints, or at least safety-critical real-time constraints on this system. So that application space determines the trade-offs you make. You design the system to be much more predictable, much more robust in that case. Versus here, you could argue that you don't want, you should not design the system in a less robust way. But you could make the trade-off that, oh, users may be more tolerant of some of the mistakes that you make in the system, right? Are you guys more tolerant of the blue screens? Do those blue screens happen still? Gray screens. I guess that tells you how long I haven't used the blue screen machines. But basically, you're more tolerant, right? But that kind of blue screen could be fatal in some other application spaces. So, yeah. OK. So in the next, in the entire course, we'll cover these trade-offs. So the trade-offs that are caused by this application space, which is ever increasing, and which will continue to increase because people will dream of new things, lead to trade-offs at every level in microarchitecture and ISA. And we'll cover ISA level trade-offs first. And then we will go into a lot of microarchitecture level trade-offs, and we'll mix system and task level trade-offs in the entire course. Basically, how to divide the labor between hardware and software. That will be an interesting trade-off. And that will be part of our ISA level trade-offs that we will cover in the next lecture also. But in the end, computer architecture is a science and art of making the appropriate trade-offs to meet a design point. I say science and art. Well, science, you could science/engineering. But it's also art, right? It cannot be a full science. I'll ask you the question, why is it art? Can you guys tell me? I can give you many reasons, but there's one reason that clearly makes it art. To me, at least. Yes?
Inspiration? Like some sort of idea just pops into your head like, wow, I could use that in some way.
So that's true. That's true. That comes in any kind of engineering also, because that's that kind of creativity you need to solve problems. I agree, but that doesn't necessarily, in a sense, that's a creative process. I guess you could argue that that makes it art. But there's a reason that it has to be art also, I think. Yes?
You don't necessarily know who the end user is and how they're going to use it, so you kind of have to make guesses at some points.
Yes.
Where you just say, this is what they might use it for.
Yes.
Because better is subjective.
Because better is subjective. I guess you could argue that you're saying the same thing. But I think what you said is exactly what I had in mind. You don't know. You don't know many things when you're designing the system. Well, let's get back to this, right? We're designing things here for which users are going to write programs. And you have no idea what kind of programs they will be, right? You're designing systems today, and they're going to be used 10 years from now. So we do not fully know the future, right? We do not fully know the users and the market. And this is actually a problem in computer architecture evaluation. Like when you design a chip, you're optimizing that chip for some workloads. What workloads should you optimize for? The chip is going to be used 5 years from now, let's say. It's going to be marketed 5 years later. Do you know what workloads there will be 5 years from now? Instagram. I don't know. Maybe. Maybe it'll be something very different, right? And it's very difficult to know this. And that's what makes it art a little bit also, because that's where you need some creativity, I think, to get to that insight. You still need to use the fundamentals, but you cannot fully model this behavior, right? And the future is not constant also. It also changes, right? So this may argue that you may want to design a more flexible system. Today's systems are very rigid, but we'll get to that later. So in a sense, this is the reason why I think it's art. You do not know the future. You do not know what these systems will be used for. In that sense, I think the term architecture is very, very appropriate. Because architecture, real architecture is art also, right? Macro architecture. And you would know that from where you are today, right? This is the machinery hall. Do we use this machinery hall as it is used in this picture? Are you guys familiar that this place was actually a boiler at this point in time? Yeah, it's not Hammerschlag Hall, but it used to be machinery hall. And if you read what is written in the entrance to the hall, it says, at the west end of campus was a small structure that housed the boiler room that functioned as the school's power plant. Below, in the rain beside the railroad tracks, a farmer's goat grazed and occasionally wandered up to eat the grass of this yet untamed end of campus. Anyway, that's not relevant, I guess. But the more relevant is the massive tower, which has become a symbol of Carnegie Mellon, was designed to disguise a smokestack. And you have this boiler room, right? And this used to function until 1975. I thought this was 1974, but the thing over there says 1975. But anyway, this is what, when you design the system, again, you don't know how it will be used. And when you architect a building, you don't know how it will be used, just exactly the same way. Now, the difference is, I think that there's a very big difference in that macro architecture and micro architecture. Macro architecture, you can change, right? You can destroy some parts of this building, as people have done, and build something else. But it's very hard to change what you actually build into these chips, unless you make it reconfigurable somehow. So keep that in mind. Anyway, this has become philosophical, but I'll see you. We'll start with ISA principles and trade-offs in the next lecture. So hopefully you'll do the readings. And we do have a lecture on Friday. So it will be Friday. Yes?